Section 4.1 is on page 252. It talks about exponential functions. We start a definition. If a is bigger than 0 and a not equal to 1, so on a number line, if a is bigger than 0, there's 0, and not equal to 1. So basically we're talking about a being either between 0 and 1 or bigger than 1, one of the two. So a is either between 0 and 1 or a is bigger than 1, and those are the two cases you need to get out of the way. Then y equal some constant times a of x is an exponential function with a base, base a. That is the base right there. And the exponent, the power, is x. X could be any number, and a is limited by it can't equal 1 and it has to be positive. Now, it's no big secret. If I take f of x equals ca to the x, if I replace 0 in for x, that would be c times a to the 0, right? And the y value would be c times 1, which is c. So 0c is an intercept. Now, really quick, if I wanted to graph f of x equal 2 to the x, the way we do this, we pick points, and I'm gonna play along and do this the long way. The purpose of this is for you to really recognize what the graph looks like. So if I put in there a 0 for x, 2 to the 0 is 1. And as you see, if I match it, isn't there a 1 sitting there? That's the y-intercept. That's very important for us. If I let x equal 1, I'll get 2 to the 1, which is 2. If I put 2 in there, I get 2 squared, which is a 4. So to the right side, it looks like a parabola, so to speak. It's really steeper, but who's counting? If I move to the left, if I pick a negative 1, I'll get 2 to the negative 1. Isn't 2 to the negative 1 1 over 2? So at negative 1, it's 1 half. And at negative 2, it's going to be 1/4, even smaller. And the graph looks like this. Now, you'll notice there's nothing you could do to make the graph cross this line. We call that an asymptote. It's a line that a graph gets very close to but never reach. This point is 0, 1, and this is called exponential growth. From left to right, this is growing. If I was to pick y equal 3 to the x, if I put a 0, 3 to the 0 is 1. If I put a 1, 3 to the 1 is 3, 1. If I put a 2, 3 squared is a 9. So to the right, this is steeper. If I put a negative 1, I'll get 1/3. So basically, the general rule is if the base is bigger than 1, then that's really how the shape looks like. 3 to the x, 2 to the x, 5 to the x. That's this case. The second case, if I really look at f of x equal 1/2 to the x. So if I pick values, this is right there. The shape looks something like that. 3 things you need: the y-intercept, the shape, and the asymptote. If I pick points between 0 and 1, well, let's see what happens. I don't know if you know that already. If I pick 0, 1/2 to the 0 is 1. If I pick 1, 1/2 to the 1 is 1/2. If I pick 2, 1/2 squared is 1/4. If I pick negative 1, 1/2 to the negative 1 is really the reciprocal, which is 2. And if I pick negative 2, I'll get a 4. If I plot these points on a number line, and again, I'm squishing this because we're not really going to do much of those, but it's important if you could recognize it. That saves you a lot of work. So let's see how this works. 0, 1, again, there it is. It passes through the point 0, 1. 1, 1/2. 2, 1/4. So to the right, it seems to be appearing this way. To the left, negative 1, 1, 1, 2. And at negative 2, 1, 2, 3, 4. So the graph looks like this. And you notice it's really the reflection of that with respect to the y-axis. The asymptote doesn't change. It's still y equals 0. There's no value of x that will make y equal 0. The point 0, 1 is there, but you'll notice if you pick a base between 0 and 1, this is exponential decay. This is dying out. This is exponential growth. This is growing. So we want to look at the graph again. I'm only covering the part of math that you need. And the way I'm going to show you how to do this is by picking 3 main points. I'll show you how that works really quick. So if you pick 3 main points, you can get the graph. That will give you these points. Or these points. And all what you have to do is, if you recognize its growth or decay, that helps you with the problem. And I'll show you how that works. Very simple to find those. Take the power, whatever the power is, set it equal to 0. Take a point above 0, that's 1, and a point below 0, negative 1. That'll do it. 4 to the 0 is 1. 4 to the 1 is 4. And 4 to the negative 1 is 1/4. So, if I take 0, 1, let's say that's it right there, 1, 1, 2, 3, 4, and negative 1, 1/4. There. You could tell that if you know this is the base is a 4, which is bigger than 1, you know this is exponential growth. So you have a good idea how the graph look like, and guess what? There it is. And if I look at problem number 10, I notice the base is 1/4. It's between 0 and 1. So I already know this is exponential decay. You could, if you like, simply just draw this, label that as 0, 1, and do an exponential decay, and me and you are very happy. You really don't have to pick any points. But if you're stuck, 3 points will do the trick. Where does the power equal 0? A point above it and a point below it. Put a 0 in there, that's a 1. Put a 1 in there. 1/4 to the 1 is 1/4, that's 0.25. And negative 1, if you take 1/4 raised to the negative 1, any fraction raised to a negative power is the reciprocal of the fraction. At negative 1, you are at 4. There it is. Shifting, I'm not going to spend a lot of time mathematically talking about shifting. I'm going to assume you're going to stick with the trick. That is, you're going to set the power equal to 0. Now, you know this is growing, right? So we know this is exponential growth, so we have an idea of the shape looking like this. Now, where does the power equal 0? Isn't that equal 0 at negative 2? Here's negative 2, you guys. Pick a point below it and a point above it. Below it will be negative 3, and above it will be a negative 1. That'll do the trick. So where does the power equal 0? A point below it and a point above it. If I put a negative 2 there, wouldn't that be negative 2 plus 2, which is 0? 3 to the 0 is 1. So this graph, negative 2, 1. this is really this. If I put a negative 3 in there, negative 3 plus 2 is negative 1. 3 to the negative 1 is 1 over 3. So at negative 1, negative 2, negative 3, you are at 1/3, assuming that's a 1. And at negative 1, if I put negative 1 there in the power, and negative 1 plus 2 is 1. 3 to the 1 is 3. Negative 1, 1, 2, 3. And this will save you. And if you're really comfortable with shifting the graph 2 units to the left, you could. Make sure you label that line for me, and everybody's happy. And this point is labeled clearly. It is at negative 2, 1. So you need to label 3 things on every graph. This, the line, and the shape. The shape, that point, and the line. There it is. And if I go to the last problem and I follow this trick, I'll notice that, guess what? Where does the power equal 0? At 0, a point above 0 and a point below 0. That should do the trick. Now be careful with reflections, but the points will give it away. If I put a 0 in there, I'll get negative 5 to the 0. That's negative a 1. So instead of this point being up here, it's really down here. Okay, I can tell there's a reflection of some sort. If I put a 1, I'll get negative 5 to the 1, which is negative 5. 1, negative 1, negative 2, negative 3, negative 4, negative 5. Okay, I can tell how that's looking. And if I put a negative 1, I'll get negative 5 to the negative 1. Isn't that negative 1 over 5? So at negative 1, you are at negative 1/5. So there, I get it. So those we need to get out of the way. Now, besides this, exponentials solve extremely complex problems. Let me start with the first one. If they give us the exponential function, we're in good shape. We just have to use a calculator. And let's see how this works. Sales in billions of dollars of Starbucks from 2009 through 2014 is given by this model. Now there are 2 variables here. Do you see that? There is S, and that is in billions. And there is T. I need to know what T is. T says, in this case it's in years, sometimes it's in days. You have to look at the problem and figure it out. Now when they say T equal 9 correspond to the year 2009, T equal 9 correspond to the year 2009. Do you see that T equals 0 will correspond to the year 2000? Are we following? If in 2009 you are 9 years old, that means you were born in 2000. That's important to know. Use the model, there's the model, to estimate the sale in 2016. If in 2009 T equal 9, in 2016, wouldn't that mean that T equals 16? And in 2020, wouldn't that mean that T equal 20? So all what you have to do is take this and say, what is S of 16? Hopefully we all have a calculator, scientific, and if I put a 16 there and throw it in my calculator, that should do the trick. So this is part A, and let me get my scientific calculator out. If I take 3.71, literally as I see it, parentheses 1.112 raised to the 16 equal, there it is, 20 point, since this is in 2 decimals, I am going to go ahead and round to 2 decimals, the least amount. So I'm going to say this is 20 point, what was it? I lost it. 28. That's good enough. That's not a problem. Or that is in dollars. Remember, this is in billions. That is 20 billion. $280 million. That would be my answer for part A. So in the year 2016, that would be the amount of sales that they did. And in case you are shocked, we sell roughly 3.1 billion cups of coffee every day. And how about in the year 2020? This is how you project how much they're going to make. You'll take 3.71, 1.112 raised to the 20th power. That would be, and again, I go back to my calculator. Now, I could go back. I don't know if you're comfortable with that. Or you could re-enter the whole thing. You should have a back button. If I delete that and put a 20 instead, there it is. That is 31.00. So we're 31.01. I'm sorry. 31.01. Just to demonstrate, you guys. You see that right there? If you're going to stop at this 0, you're going to round because that's 7 or more. And let me show you the difference between you putting that 0 or not. The actual sales will be 31 billion 010. That number you were going to take off, that's actually $10 million. And there it is. So if they give us the formula, it's fairly simple and nice to play with. And let me do another problem. I really made this up to match your number 23 in the homework because I don't want you to have any surprises. And I thought there's one more. Good. Now, inflation rate with an annual rate of 1.5%. Again, you don't have to worry about that over 10 years because they gave us the formula. You only have to worry about this when they don't give you the formula and you need to come up with it. And you notice those are exponential functions. Did you notice that? That's growing. Since the base is bigger than 1, that's exponential growth. That's important to know from a business point of view. Well, it says over the next 10 years. So we know that T is in years. Good. T is in years. Because there are two unknowns. There's T and there's P. The approximate cost, C is the cost. And that's probably in dollars, of course. Of goods or services during any year in the decade is given by this, where T is the number of years and P is the present value. P is the price right now. The cost right now. This is how much it's going to cost us now. The price of an oil change for a car is right now, presently, that's P, $24.95. Estimate the price $10 from now. Well, we just have to use the formula. The cost in 10 years' time will be P. We know what the price is right now. They gave it to us. $24.95 times 1.015 raised, and T is 10. And if I throw this in my calculator, and here's my calculator again, I'm taking 24.95 multiplied by 1.015 raised to the 10th power. And I'm getting 28.96. If it's money, you round to 2 decimal, $28.96. That would be the cost of an oil change 10 years from now if we are increasing at a rate of 1.5% inflation. That's really important to know. And I have one more. I wanted to do a problem like number 25. 25 talks about business. 26 is identical, but it talks about concentration of. So bottom line is, you get this amount, this set amount, drug concentration following injection. When you get injection, the concentration of drug in the bloodstream is 300 milligrams per liter. So you start with 300, whether it's medicine, let's say $300, you know, after T hours. So this problem works for hours. Here, T is hours. It's important to know that. And C is, the concentration is 75% of the level of the previous hour. Every hour, you lose 25% of what you have. So you end up with 75%. Find a model for the concentration. This could be cost. It could be I bought something for $300 and I'm losing 75% of it every year. Write a model for that. Well, the model would be whatever you start with, that's the initial amount, times 0.75 raised to the t. In this problem, t is in hours. And if I get the equation, I'm done. So keep in mind how this works. If I start with 100, an hour after, I'm going to only have 75. An hour after, I'm going to have 75% of that. So this is not as simple as you subtracting 25 every time. It's really complex. That's what exponentials do. And part B on this problem, we say, well, they're asking, oh, sketch a graph of the model. If I want to sketch a graph on this model, what do you notice? Where do you start? Set that equal to 0, or simply, isn't this the initial amount? Say that's 300, right? Isn't this exponential decay? So doesn't that look like this? Except this part is not allowed because we're talking about concentration. So most of the applications, you're only looking at quadrant 1. That's the graph. This is going to decay. Eventually, it's supposed to get very close to gone but never gone. So there's really no A or B. I'm going to set this to be A. B is the graph, let's say. It's right there. And C. Sketch the graph of the model and determine the concentration of the drug after 8 hours. Well, hopefully we're comfortable by that now. What's C of 8? In 8-hour time. And if I get my calculator again and take 300 parentheses point 0.75 raised to the 8th power, enter, I'll have 30.03. 30.03, and again, this problem's concentration, it's going to be milligrams. Your problems are going to have money and business. Milligrams per milliliters. So the units are right there. And let me give you the homework. There's the homework. And number 3, if you could do that on a scientific calculator, that would be great. I just want to make sure you know how to plug that in.